All right, I think it's 5 past, so we can start. We're very happy to have Mengjie Qian from the University of Cambridge giving a talk on grammar error correction. She is currently a research associate in the University of Cambridge, working with both Mark and Kate. And she was a PhD a while ago, I guess, from University of Birmingham. So we're very happy to have her today. Yes, Mengjie, take it away.
Great. Thank you for the introduction. So thank you everyone for joining me in this talk today. And I know some of you may not be in the UK time zone, so it may be late for you already. So in today's talk, I'm going to talk about two things. One is a speak and improve challenge, and the other is advances our work in the end-to-end spoken grammatical error correction. So the first thing, speak and improve challenge. This is a challenge we organized in for this year and hosted with Slate in August. So this talk was originally scheduled before the Slate, but for some other reasons it was rescheduled to now. So some of the audience may have been to Slate and may have heard some of the work from us and from other participants about Speak and Improve Challenge. Okay, so the motivation for us to organize this challenge is that we know that worldwide there are around 1 billion learners of English as a second language, and we know that automating the spoken language assessment and feedback will help support L2 English learners. But the problem is that there are limited high-quality label data, which makes it difficult for groups to do research in this space and also difficult for them to compare experimental findings. So to address this, we release a new annotated corpus called Speak and Improve Corpus 2025. In this corpus, we include different annotation types, and it's collected from a platform, which I will introduce later, with free spoken L2 learner English. And we organized a challenge with ISCA Slate workshop, 2025 August. And then in this challenge, we encourage participants from worldwide to do different tasks related to language learning and assessment. So the corpus was collected from the Speak and Improve Learning platform. And here is a link for the website. And this platform is free to use as a practice tool. And then we have multiple versions for this platform. In the beginning, version 1, learners need to take the whole test. The test have different parts, including answer questions about yourself, read aloud, give opinions on certain topics. And then to get a full score, you need to go through, like it will have a score for each part, but to get a complete test, you need to go through the whole test process from part 1 to the end. And in the version 2, it's more flexible. You can choose a specific practicing type and just practice that skill. So over the years, there are more than the learners have tried this platform coming from over 150 countries, and we have seen more than 400,000 learners. So the corpus we released for this challenge are mostly collected from the version 1 platform. And the data annotation was done by some human experts, and it includes three phases. The first one is scoring. So the annotators will listen to the audio recordings and give a holistic spoken language assessment score for each test part. And the score will be between 1 to 6, roughly equivalent to the CEFA A1 to C levels. And then in phase 2, the annotators will transcribe the audio, aiming to generate the text, what the learner have said accurately. And then in phase 3, which is error annotation, The aim is to generate a grammatically accurate transcription of the learner's intended speech. And at this stage, the annotators only work with text, do not listen to the audio. And here are some statistics for the corpus. This corpus has speakers from diverse from worldwide, but we don't have the L1 information for the speakers. And then the proficiency levels is from A2 to C1. And then we have around 300 hours of recordings, all with holistic proficiency. And then over 700 hours manually transcribed speech, and over 50 hours fully annotated with grammatical error correction text. So for the challenge, we organized 4 tasks. And here on the right, we showed a pipeline. And then this pipeline shows the process of the steps and also the relationship between the tasks. We start from the audio recordings. And the first step is to generate text from the audio recordings. And this is the ASR step, automatic speech recognition. And then in this step, we aim to generate accurate transcriptions, meaning that it may have disfluent in it. And then once we have the disfluent transcriptions, we use a text-based spoken language assessment model, SLA, to generate a holistic score for the audio. So in the challenge, we provide, so SLA is the second task in the challenge, and we provide the baseline, which is ASR plus SLA cascaded pipeline, but we encourage participants to work with like end-to-end models as well. And then another direction is to do grammatical error correction. To do that, we also start from audio and then ASR to text. And then once have the disfluent transcriptions, we use a disfluency detection model to remove the disfluencies in the text and generate fluent transcriptions. And on the fluent transcriptions, we use a text-based GEC model to generate grammatically error-corrected transcriptions. So this is basically the baseline for spoken GEC system. And so another way is that we have the GEC transcriptions. We want to provide learners with feedback. So this is task 4, spoken grammatical error correction feedback. I will tell you more on this later. So for each of the tasks, we have a closed track and an open track. In the closed track, the participants can only use pre-trained models from the baseline system, provided dataset, and name the datasets for training. And then in the open track, any publicly available data or pre-trained models can be used. So, and for the challenge, we provide baseline systems for each of the tasks. So so on the right, it roughly shows the baseline pipelines for each task. And for the ASR, we use OpenAI Whisper Small model as the baseline. We didn't choose the large ones because we understand that for some groups, they may not have large computational resources for them. So we want to choose a reasonable, a baseline that is reasonably good, but not too big. And then for the SLA, the text part, we use the BERT-based model as the text grader. And then for the spoken GEC and the spoken GEC feedback, the models are the same, it's just the evaluation stage is different. And in that, we use a BERT-based model, BERT-based uncast for the disfluency detection, and BERT-large for the text-based GEC. Okay, that's the challenge, the tasks, and the data. And now let's look at some results from the participants. For the ASR, I'm only showing the top 3 results here. So for the ASR, we have around 10.84% as the word error rate. And in the closed track, the best result is 6.47. And then for the open track, the best result is 5.05. We can see that the word error rate reduced largely by the participants. And then, so what we observed from this task is that in the closer track, the larger the whisper model used, the lower the word error rate, which is aligned with what we would expect. And in the open track, there are various ASR architectures with fine-tuning strategies being used. And interestingly, none of the teams have added further data, which kind of suggests that the speak and improve corpus is big enough for the ASR task. And then for the spoken language assessment task, we use RMSE as the main evaluation metric, rooted mean squared error. And then for the baseline, we have 0.44 as the RMSE score. And then in the closed track and open track, the winning team is both from the Duolingo USA, and the results are quite similar. In the closed track, we got 0.368, and the open track, we got 0.364. So what we observe from this is that we noticed that in the closer track, teams combined acoustic and textual features using diverse modeling strategies. And then in the open track, teams used additional models, data resources, and multimodal strategies. So this is different from the ASR task. And then the top team uses a BERT-based text grader trained on ASR transcription. It's still a cascaded pipeline, but the ASR model and the text grader is different from the baseline. And then for the spoken gag and the spoken gag feedback, unfortunately, we only had one team participated in these two tasks. And on the top, it's a spoken gag, and the evaluation metric is word error rate. And we can see that in the closer track, it didn't outperform the baseline. And in the open track, there are around 3% reduced in the word error rate. In the spoken gag feedback, the F0.5 score improved for both the closed track and open track. So what we see from this task is that, first there was only one team participated, which is a bit disappointing. And then in the closer track, the team only replaced the ASR system in the pipeline with a larger version of the whisper model. And in the open track, they replaced the whisper model and the text-based gag model, but the pipeline is still a cascaded pipeline. Okay, so for this part, the Speak and Improve challenge, we released the Speak and Improve corpus, which is still publicly available for research use purpose. The license has changed. We had a different license for the challenge, and now we are using a different license for research purpose. And you need to agree with the license before downloading the corpus. And in the challenge, we organized 4 tasks, and participants have significantly improved upon the baseline performance on the ASR and SLA tasks. And then we, the spoken gag and the spoken gag feedback lack attention despite their importance. So in the next bit, I will talk about end-to-end spoken grammatical error correction. So this is an important topic in language learning area. But as we can see that there are not so many groups have been working on it so far. So we want to attract attention in this domain and encourage the community to work on this task. So first of all, what is spoken grammatical error correction? The aim of GAG is to produce grammatically correct sentences. For example, if we have an original sentence, learning several languages is very better. And the corrected sentence could be learning several languages is way better. And when it comes to spoken gag, it is more complicated as speech contains disfluencies such as hesitations, repetitions, false starts, or accented speech. And because of these, it is more challenging. For example, as shown in the example, the original sentence could be, learning several languages is very better. So it has hesitations or partial words in the sentence. And then the corrected sentence will be still similar as a GEC version. Learning several languages way better. So yeah. Because of this, we can see that spoken GEC is more complicated than GEC, which is based on text only. And traditionally, we use a cascaded pipeline, which has 3 components: ASR, disfluency detection, and GEC. This is the same as the baseline we provided for the Speak and Improve challenge. So the ASR will aim to produce accurate transcriptions which has different words in it. And disfluency detection is based on text and try to remove the disfluencies in the text. And GEC is based on is trying to correct the grammar. So this pipeline works quite well, especially for disfluency detection and GEC. There are large text corpus available, so the training data is larger, but it also has some limitations. One is that the ASR errors might propagate through the pipeline. And also there is lots of information like the intonation or speaker information or emotions in originally more in the acoustic side may not be propagated to the text to the DD and GEC. So in one of our work, which is published in ICASP 2024, we propose an end-to-end spoken GEC approach. The main idea is to fine-tune Whisper on 3 different sets of transcriptions separately to generate ASR transcriptions in different formats. So let me explain it a bit more on different models. So when we look at the pipeline, we have 3 components, and the first is ASR. So the simplest idea with Whisper is to use Whisper for the ASR model and try to produce accurate ASR transcriptions, which works well. But then we call this Whisper disfluent. And then we think maybe we can use Whisper to combine the ASR and the disfluency detection and ask the model to produce fluent ASR transcriptions directly. And we call this Whisper fluent. And then thirdly, we ask the model, one single model, to generate grammatically correct results directly to replace the ASR, DD, and GEC 3 steps. So we call this Whisper GEC. And so that's the basic idea for the end-to-end Whisper GEC model. And to show how the end-to-end spoken GEC systems perform, let me explain how we evaluate an SGEC system first. To evaluate spoken GEC, one metric is word error rate. For example, if we have the manual GEC transcriptions, we compare the automatic GEC transcriptions, which was produced by the Whisper end-to-end Whisper GEC model, and we compare these 2 transcriptions and calculate the word error rate. And then another important aspect is for evaluation is feedback. We don't want to give learners corrected text only. We also want to provide feedback to learners so that they can actually learn what grammar errors they have made and how they can improve. So to do this, the spoken GEC feedback is evaluated based on edits and using metrics such as precision, recall, and F-score to evaluate. So here I'm showing an example. So we have the manual fluent transcription and a manual GEC transcription. By comparing the manual GEC transcription against the manual fluent transcriptions, we can know that what edits you need to make to correct the transcription. And then the sets of edits, we call it reference edits. And we also have the automatic fluent transcription and automatic GEC transcription from the Whisper models. And then we call this hypothesis edits. And once we have the 2 sets of edits, we can compare these 2 and calculate the precision, recall, and F-scores. So in this example, the edit score has hypothesis edits has an extra edit, which is an insertion of the word. And then in the in the experiments, the F0.5 is chosen. This is to prioritize precision over recall, try to reflect the importance of high confidence feedback in learner-facing applications. And then in our work, we tried different methods to improve spoken gag and feedback in the end-to-end settings. The first idea is data augmentation. So the main idea is to address the lack of annotated data issue in end-to-end spoken gag. And there are limited annotated spoken gag data, but audio data are largely available. So we use a pipeline to generate pseudo-labels for audio. And the pipeline used was the best model in our initial experiments, which is a partial-cascaded system, including the Whisper Fluent model to generate fluent transcriptions, plus a text-based gag model. Yeah, so, and in this method, the aim is to boost the spoken gag performance, meaning the word error, and then we expect that the corresponding feedback performance will be improved as well. And the second method is prompting whisper. The main goal is that we want to provide additional context information to the end-to-end whisper gag model so that the model can learn better how to provide feedback. As when calculating the feedback performance, the gag transcriptions is compared with the fluent transcription. And to do this, we use the fluent transcriptions from a Whisper Fluent model as the prompt to the input of the decoder. Yeah, as I said, this is mainly to improve the, we aim to improve both the spoken gag and feedback performance. The third method is aligned gag reference. So yeah, this is mainly to improve the feedback performance. The main idea is to modify the gag reference to align with fluent transcriptions. Let me explain this in detail. So when we calculating the edits, we will compare the gag reference with the fluent reference, and then this will give us what edits you need. And assume we have a model, an end-to-end model, which can produce perfect gag reference, and we will compare that with the fluent hypothesis to get the hypothesis edits. But if the fluent hypothesis is from an automatic model, and it will have errors. So in this case, even the end-to-end model is perfect, it may still produce additional hypothesis edits. Like in this example, if we compare fluent hype with gag ref, there are errors, like there will be a substitution or replace error from cat to rat, and an additional deletion error with the word the second. The errors coming from the ASR error, like by comparing the fluent hypothesis with the fluent ref, you can see the automatic fluent model is not perfect, it has errors, and these errors becoming like forget as the edit error. So because of this, we think that if we can modify the gag reference for training the spoken gag model, the end-to-end spoken gag model, we can handle the ASR errors in the fluent transcription and make it to produce feedback more accurately. So we have two versions of modified gag reference. One is called mild. So we only look at the substitution errors in the gag. So we compare the fluent hypothesis with the gag reference, and we only look at the substitution errors and modify the gag reference according to this. And in the second method, we call it strong because we make more modifications to the reference. We will look at all the error types, including insertion, deletion, and substitutions, and then makes these changes to the GEC reference. So this is for this GEC reference is used for training the end-to-end model. When evaluating, we're still using the original GEC reference. Okay, and then the fourth method is added confidence estimation and filtering. So what means by this that the motivation of this is that we know that the automatic models, Whisper Fluent and Whisper GEC, they will produce words with low confidence. So as a result, the edits may include low confidence regions as well. So this will result in low feedback evaluation. So we propose a method to estimate edit level confidence score. So here is an example. We will get the word level confidence for the fluent transcription and the GEC transcription. And then there are different ways to calculate the edit level confidence score. One method is just to average it. So we will look at the edits and the words corresponding to this edit. So one example is like there is an insertion of vocabulary up in the GEC hypothesis. And in this case, there is no corresponding word in the fluent transcription. We will just assign the score 1 in this case. And then the GEC confidence, we can get it from the model. And we just average the scores to get the overall edit level score. And then for the second example, the replacement error from holidays to holiday, we got the confidence score associated with the fluent words and the GEC words, so we can calculate the confidence based on this. So in our experiments, we tried a few different ways to calculate the confidence score for the edits. So for the experiment, we mainly experimented on lingual scale and speak and improve dataset. As I introduced before, speak and improve is publicly available. Lingual scale is not. These two data have similar test formats, which includes different parts. Like part 1 is answer some questions, part 2 is read aloud. I will not go into the details. And then CEFR levels are from A2 to C1. And then the lingual scale has around 77 hours labeled training data, and it has 2,500 unlabeled training data. And speak and improve, we only use the dev set for evaluation. We didn't use the training data for the experiments on speak and improve. And for the models, we have Whisper Fluent, which is Whisper fine-tuned on menu fluent transcriptions. And we have Whisper GEC, which is Whisper fine-tuned on menu GEC transcriptions. And we experimented on 2 versions, with Whisper small.en and large v2. And for the text-based GEC model, it's based on a BAT model and fine-tuned in 2 steps. First is text-based corpus out domain, and then second is the lingual scale. Okay, so let's look at some results. Here I'm showing the baseline results and results with pseudo-labeled data. So the first 2 rows are 2 baseline models. The first, the cascaded Whisper disfluent plus DD plus GEC, and the partial cascaded system, which is Whisper Fluent plus GEC. These 2 models, they already have quite decent performance on both the lingual scale and speak and improve. And then the third row is Whisper end-to-end Whisper GEC model trained on labeled lingual scale data. We can see that on the speak and improve we didn't train, we still trained on lingual scale. And then we can see that it has a degradation compared to both baselines. So on the small.en version. And then when we train the end-to-end model on unlabeled data first and fine-tune on the labeled data, we see improvements on both the lingual scale and speak and improve datasets on the small.en version, which is good. But then when the model size increases on the large V2, the benefits of data augmentation with pseudo-label data diminishes, which is quite disappointing. Yeah, so, and then when we experiment with prompt-based training, we focus on the large V2 model because it has better performance. So the first line is baseline, and the third row is training the end-to-end model with prompt. We can see that training with prompt can improve the performance slightly on both the linguist scale and speak and improve. So here are the word error rate, which is for the spoken gag evaluation. And for the feedback, we can also see that training with prompts outperform the whisper gag model on all metrics. Compared to whisper fluent plus gag, the partial cascaded system, the whisper gag plus prompt model achieves comparable F0.5 score, which is slightly a bit disappointing given that on the word error rate, the improve is quite large. But then, like compared to on the word error rate, the performance of end-to-end model training with prompt is quite good compared to the partial cascaded system. But on the feedback, it didn't improve that much. So it kind of shows that feedback generation is more challenging. So then here we are aiming to improve the feedback performance. So these results are using the aligned gag reference. The original is training the end-to-end model with the original reference, and the mild is training with a mild modification of the reference, and strong is a strong modification for the gag reference. We can see that with the mild, the word error rate roughly maintains, and the feedback improves on both the linguist scale and speak and improve. And with the strong modification, the feedback improves further, but there is a degradation on the word error rate. So yeah, so so basically it says that you need to consider the trade-off between the word error rate and the feedback when you are modifying the gag references. And here is the results, feedback results with confidence score. We are showing experiments in different settings, like the whisper gag model without prompt, and with whisper gag model with prompts, but in different training reference, original, mild, and strong. In all cases, we can see that using edit confidence score can help with the feedback performance, which is very good. And we also notice that on a model which is has stronger performance, the improvement that edit confidence score can bring us will reduce slightly. Okay, so here is the figure we just showing how it looks like with the precision recall and F0.5 score when we are sweeping the confidence threshold. And increasing the threshold will improve the precision because this will discarding more uncertain edits, and the recall will decline. And the best F0 point score is around 0.667-ish. So this suggests that moderate filtering will help suppress noisy edits, and it will not lose too many valid corrections. Okay, so these results, the previous results are shown on Speak and Improve dataset, and in the Speak and Improve challenge, we released the evaluation set, which we released around March, and I'm showing some results here so that we can compare our methods with participants in the challenge. And on the Speak and Improve eval set, I'm showing some of the best settings, not the complete experiments. So we can see that for the baseline, we have word error rate of 14.37 and F0.5 score of 42.24. And with the mild and strong, the word error rate are reduced and the feedback are improved. Yeah, the observation is similar as on the dataset with a strong modification of reference. The word error rate will increase slightly, but the feedback will also improve. So there is a trade-off you need to consider. And yeah, this is just to show our results compared to the participants in the challenge. We can see that in both word error rate and feedback, we kind of improved quite a lot. But also, like we understand that the F score there is still a large space for us to improve, and yeah, we want to attract more people working on this task. Okay, so for conclusion, we have proposed end-to-end spoken gag systems, and we want to focus on the feedback aspects. And we proposed the different complementary techniques to improve both spoken gag and feedback. And with these methods, we managed to make the end-to-end model outperform the cascaded and partial-cascaded pipelines across different metrics. And generating high-quality feedback is still challenging. We still need to consider the trade-off between transcription accuracy and feedback precision. Yeah, and here are some papers relevant to this work. So if you have any other questions, yeah, you are welcome to ask. Thank you.
Okay. Thank you, Mengjie, for the great talk. Yes. We have plenty of time for questions. So, don't be shy. Feel free to just unmute yourself and then ask questions.
Okay, I can start. I was wondering, I was thinking there are many ways to correct a sentence to be more grammatical. Do you have variations in your annotations, or how did you handle that?
That's a very good question. I think for people interested in this task, that's definitely some direction to look at. In our case, we only have one version of the corrected sentences because we are not generating the annotations for the data. The data is annotated by Cambridge University Press and Assessment. They have specialized annotators to do this task, so they produce the transcription to us, and they only they listen to the audio and they just try to find the make minimal edits to make the grammar correct. So that's what they asked to do. So they just produced one version. But yes, in reality, when a learner is make some mistakes, there are multiple ways to correct it. And maybe the minimal edits may not be the most comfortable or most familiar ways for them to correct. So that's another direction to look at. And also, when we have multiple corrected versions, how are you going to evaluate it? That's also another question to consider in this domain.
More questions? Well, while the audience is thinking, I'll be the reviewer number 2 and ask the elephant in the room. Why not use large language models for grammar error correction?
We did. So first of all, the large language model, there are two questions. So for large language model, it's performing on the text level. So it's still you still need to have the initial steps, speech recognition and different dissection, or at least the speech recognition. So we've done some experiments on that. It didn't work so well. like it didn't outperform our models. And also, second, you can use a speech large language model as an end-to-end model to perform this task. We did some initial experiments on this as well. The training is not so easy for these models to perform this task.
Okay, interesting. Well,
yeah, we are continuing working on this domain. So maybe we will find a way to make use of speech large language models or large language models in some way that is not training intensive, because one advantage of these models is that they have been already trained on large quantity of data. So ideally, we want to use them in a zero-shot fashion, but in reality, they don't work so well in zero-shot fashion for some specific tasks like spoken gag. So we still need to come up with some ideas to improve the performance without heavy training.
right. I remember seeing a few successes for rescoring ASR output with LLMs. And so they seem to have the capability of doing that. It's probably just, yeah, there's some subtle differences between correcting ASR output and this task.
We've done some work using large language models for ASR error correction. It's slightly different. So like, yeah, one is like machines are making some mistakes, and the other is like human are making some grammar errors. Specifically grammar errors when they are learning a language. So there are some subtle difference. And also, when it comes to ASR error correction, we can provide the model with more information about the model, about the ASR model. For example, we experimented with unbiased list from the ASR, which works quite well. But for learners, we cannot ask the learner to produce different versions of grammar errors, because like that's not the aim. That the aim is for them to produce the grammar corrected version. It's fine to provide multiple versions of corrected version, but it feels odd to ask for multiple incorrect versions. So yeah, it seems very similar, but when it comes to models and trainings, it's quite different.
Can I ask questions?
Yes, go ahead.
Yeah, it's nice to hear you have excellent result coming. And as far as I understand, your main work is trying to figure out new edit distance measure and how you manipulate the data in that sense. But the other point I'm actually interested in is there any specific model architecture for the fine-tuning? Did you use LoRa or something different on the FISP model itself, or BOT and BART models?
So we've tried, so in terms of model architecture, we used Whisper because it works quite well in many settings, and we've tried a few other models as well. This one works relatively stable. And so in terms of training methods, we tried direct fine-tuning and LoRa as well. So LoRa always performs slightly worse. I think it depends on what your goal is. On some tasks, LoRa fine-tuning, the performance from LoRa fine-tuning is already good enough. So you can use LoRa fine-tuning to save some resources or time, and the results is still decent. It's already decent. But for the spoken gag task, we can see that the word errors may be fine, but for the feedback, 45% is okay, like compared to what it was before, it improves quite a lot, but it's still like, it's not, there is a big gap. We tried to look at using the ground truth transcriptions, and can give us around 70 F0.5 score. So there is still a big gap, and I think using LoRa will provide a slightly worse result. So that's not the focus at this stage. Yeah.
All right, thank you.
I actually also have some, a similar feeling as well, because you mentioned at some point that you were modifying the references and then incorporating the confidence score, right? So I feel like it's just that the references needs to include some kind of uncertainty. And so it almost feels like you can do some kind of discriminative training on Whisper in order to incorporate all of these things together. Well,
I think definitely there's more we can do in this direction, but also it's difficult because the feedback, unlike a lot of tasks, the feedback is based on the two aspects, the fluent transcription and the GEC transcription. So you need to provide both informations to the model. So how to set up the model to train and look at both directions, it's not so straightforward.
oh yes, that reminds me. When you do the prompting, wouldn't that confuse Whisper? Because it's not trained with prompts, right?
It was trained with prompts.
Okay.
So you have different settings, like you can train the Whisper GEC model without prompts and test it with the prompt. And also you can train the model with prompt and test with or without prompt. So I think we tested the different versions. It is actually learning from the prompt. That's the conclusion. So when you train the model with prompts and test it with prompt, it can actually learn something. So yeah.
Oh, okay. Yeah, I got it. I thought you were just using the vanilla Whisper because that one is definitely not trained with.
No.
Yeah, so okay.
Because we want the Whisper model to generate GEC transcriptions, so we need to train the model anyway.
Any more questions from the audience? No? Okay, I'll ask one final long-term question, I guess. Have you actually tried sending these feedbacks and do some usability study on users, like L2 learners?
No. I think this will be important. But this is more from the pedagogical side, and like you said, it's quite long term. So I think maybe at some stage we are satisfied with our performance, then maybe we will move on to that stage. But at the current stage, we feel that we are kind of okay with the performance, but we believe it's not good enough. So and we are trying to work more on this direction. So I think when we have the feedback performance close enough to the ground truth, then we can consider that. Yeah.
All right. Any more questions? Final questions? No? Okay. If not, then we can thank the speakers again. Thank you so much, Mengjie, for giving the talk. And we will continue to have talks next week. So I think is Alexander still here? He is actually. So we will have another talk next week about target speaker ASR. So stay tuned and I'll send out the announcement soon. And let's thank the speaker again, and we'll see you next week.
Thank you very much. Thank you.
Bye.
See you.